thunderstorm? That sudden, brilliant flash of lightning, followed by a sky-shattering boom of thunder? It's one of nature's most spectacular and intimidating displays. But have you ever wondered what's actually happening up there in those dark, swirling clouds? What causes that incredible light show and its booming soundtrack? Today, we're diving deep into the electrifying science behind thunder and lightning. Let's get started. So, it all begins inside a storm cloud, specifically a cumulonimbus cloud. These clouds are massive, towering giants, often stretching miles up into the atmosphere. They are turbulent places, full of water droplets and tiny ice crystals swirling around violently. As these particles move, they constantly bump into and rub against each other. This friction is key. Acts just like when you rub a balloon on your hair. Electrons, which are tiny negatively charged particles, get knocked off some of the ice crystals and stick to others. This constant shuffling of electrons creates something called charge separation. The lighter, positively charged ice crystals are carried upward by the storm's powerful updrafts, gathering near the top of the cloud. Meanwhile, the heavier, negatively charged particles, like graupel, which are soft ice pellets, sink towards the bottom of the cloud. So now you have a giant, natural battery in the sky, a positive charge at the top and a negative charge at the bottom. The ground below the storm cloud also becomes positively charged, creating a massive electrical imbalance between the cloud and the Earth. Nature always seeks balance, and this electrical imbalance is no exception. The air between the cloud and the ground usually acts as an insulator, preventing electricity from flowing freely. But when the charge difference becomes too extreme, the air can't hold it back any longer. The insulating capacity of the air breaks down, and this is when the magic happens. A massive, uncontrolled electrical discharge occurs to neutralize the charge. We see this discharge as a flash of lightning. So, how does that flash actually form? It's not just one single bolt. It's a fascinating, multi-step process. First, a faint, negatively charged channel, called a stepped leader, begins to snake its way down from the cloud towards the ground in a series of short, staggered steps. It's almost invisible to the naked eye. As this leader gets closer to the ground, the positive charge on the surface reaches up to meet it, often from tall objects like trees, buildings, or even people. These upward-reaching positive channels are called streamers. When a downward leader connects with an upward streamer, it completes the circuit. Suddenly, a powerful electrical current surges back up from the ground to the cloud along this newly formed path. This is the return stroke, and it's the incredibly bright, visible flash of lightning that we all recognize. This return stroke is hotter than the surface of the sun, reaching temperatures of up to 30,000 degrees Celsius, or 54,000 degrees Fahrenheit. It all happens in a fraction of a second, which is why we see it as a single, instantaneous flash. Sometimes, you might see a lightning flash flicker. This is because multiple return strokes can travel up and down the same channel in quick succession. Now, lightning doesn't just happen from cloud to ground. In fact, most lightning, about 75% of it, happens entirely within a cloud, called intra-cloud lightning. This is the discharge between the positively charged top and the negatively charged bottom of the same cloud. You often see this as a bright flash that illuminates the whole cloud from within. There's also cloud-to-cloud lightning, which is a spectacular discharge between two separate clouds. And sometimes, in rare cases, lightning can even travel upwards from the top of a storm cloud into the stratosphere. These are known as sprites and jets, and they are incredibly difficult to see from the ground. Okay, so we've got the lightning, but what about the thunder? Where does that deafening roar come from? Well, thunder and lightning are created at the exact same time. The thunder is a direct result of the lightning. Remember how we said the lightning channel is hotter than the surface of the sun? This intense heat causes the air surrounding the lightning bolt to expand explosively, faster than the speed of sound. This rapid expansion creates a powerful shockwave in the air, similar to a sonic boom. That shockwave is what we hear as thunder. You might be thinking, if they happen at the same time, why do I always see the lightning before I hear the thunder? That's a great question, and the answer lies in the different speeds of light and sound. Light travels incredibly fast, at about 300 million meters per second. For all practical purposes on Earth, we see a lightning flash almost instantaneously, no matter how far away it is. Sound, on the other hand, travels much, much slower, at only about 343 meters per second in dry air. Because of this speed difference, there's a delay between when you see the flash and when you hear the boom. You can actually use this delay to estimate how far away a storm is. Just start counting the seconds between the flash and the thunder. For every 5 seconds you count, the storm is approximately 1 mile away. So if you count to 10, the lightning struck about 2 miles away. If you see the flash and hear the thunder at almost the exact same time, you know the storm is very, very close, and it's time to be in a safe place. The sound of thunder can also vary a lot. Sometimes it's a sharp, loud crack, and other times it's a low, long rumble. Why is that? The sound depends on your distance from the lightning bolt and the nature of the bolt itself. If you're very close, you'll hear a single, loud crack, because the sound from the entire length of the channel reaches you at roughly the same time. But if you're farther away, the sound from different parts of the long, crooked lightning channel will reach you at slightly different times. The sound also bounces off the ground, hills, and buildings. This combination of delayed sounds and echoes is what creates the long, rumbling effect we often associate with thunder. So from the tiny interactions of ice crystals in a cloud to a superheated channel of plasma and a resulting sonic boom, the science of thunder and lightning is a powerful example of physics at work on a massive scale. It's a beautiful, awe-inspiring, and frankly, a little terrifying reminder of the immense power that nature holds. And while it's amazing to watch, always remember to do so from a safe location. The best place to be during a thunderstorm is indoors. Next time you see a flash of lightning tear across the sky and hear the thunder roll, you'll know exactly what's happening. It's not just random noise. It's the sound of our atmosphere being superheated and expanding in an instant. It's the grand finale of an incredible atmospheric electrical event. Thanks for joining me on this journey into the heart of the storm. If you enjoyed learning about the science of nature's fury, make sure to hit that like button and subscribe for more deep dives into the world around us. Stay curious, stay safe, and I'll see you in the next video.